Okay, have you ever wondered how astronomers know what the mass of other planets and other objects in the solar system and the universe is? Well, the most common way of doing it is to observe the gravitational effects of that object. And then you can infer its mass from Newton's law of universal gravitation that we've learned about. So let's consider this example of the largest asteroid in our solar system. It's called Ceres. And imagine that an astronaut travels there. We haven't had any astronauts land on asteroids yet, but we have had space probes do it. No people yet, but maybe someday that'll happen. So imagine that an astronaut travels to Asteroid Ceres and drops a rock from an initial height of 10 meters above the ground, above the surface, and has a stopwatch and times that fall at 8.06 seconds. From that information, we can figure out the acceleration of gravity on that asteroid. We can figure out the g value. G is 9.8 meters per second squared on the Earth's surface, but as we learned in the previous lesson, g depends on the mass of the object and the distance from the object's center. Once we know that, we'll figure this out using our good old kinematic equations, by the way. And in part B, then we can use Newton's law of universal gravitation to figure out the mass of the asteroid, given that its radius is known. You can figure out the radius just by observing it with a telescope and making a size estimate. And then in part C, we'll figure out that new value of the gravitational free fall acceleration if you start 50 kilometers above the asteroid's surface. All right, so in part A, we know an initial height, we know a final height, we know a time, we know an initial velocity, 0 because you drop the rock, and we want to find the acceleration. I'm kind of using this interchangeably with this. So we'll use y final equals y initial plus v initial t plus 1/2 a t squared, our favorite kinematic equation. Y final 0, y initial is given. I'll keep this in symbols for now. V initial t is 0. So we can solve this equation for A. And it gives us a value of minus 3.08 meters per second squared. And according to our convention for g that we've always done, we'll consider g to be the magnitude of this acceleration. So that's g for an asteroid. Notice it's a lot smaller than the free fall acceleration on planet Earth. A lot smaller than 9.8. If you dropped a rock, it would take forever to fall down. Looks like it would take like 30 times as long to it's falling 30 times slower. Okay. Part B. Actually, it takes square root 30 times as long. All right, find the mass of the asteroid. So we learned this relationship that g, the free fall acceleration, is given by the universal gravitation constant times the mass of the object, writing a subscript c for Ceres, the asteroid, divided by the distance to the center of the object squared. So we'll turn this equation around. mc equals little g times r squared over, nope, over g, yeah, over capital G. And you plug all that in, and you get 1.2 times 10, 21 kilograms. Okay, so that's a big object. It's still several thousand times smaller than planet Earth, but a big chunk of rock nonetheless. Last question. What if instead of standing at the surface of the asteroid, you're 50 kilometers above the surface? Now how fast does that rock accelerate when you drop it? So we use our expression for g. I'm going to put a little prime symbol here to represent that we're talking about a different situation than we were when we used that other g value at the surface. Now we're talking about being at some height. So it's capital G mc divided by the new height above the surface. So if we're 50 kilometers above the center now, that means that the distance is the radius plus the height. And we're given that value for the height. They tell you in kilometers. Make sure to turn it into meters when you plug in these numbers. And you should find that it's 0.255 meters per second squared. So now we're falling considerably more slowly than before. All right, and that's how we can do measurements of mass and measurements of gravitational acceleration for astronomical objects.